Welcome everybody. Good to see you. We still got a little bit of time left. The seniors are finished up. They're not going to be in class today, but we are, and we're going to do something fun. We are finished with the actual curriculum, right? We've already, we're just waiting on the semester final ourselves, which is 2 weeks from today. And almost exactly, it's like 9:15 on that Tuesday morning, right after the 3-day weekend. But hopefully you'll be exempt, right? Most of the seniors are exempt. And we had, how many seniors did we have in this class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We had like 14 seniors in here, and only 4 of them had to take it. Most of them are exempt. So hopefully you'll be exempt. You guys have done a great job of keeping up on all the work. I don't know that you hardly anyone has any missing assignments. So this will be our last assignment here. We will meet next week. And I have something else fun we'll do during class, but we'll meet next week. But this week we have kind of a fun assignment. I've gone, since we finished up our curriculum, I'm going in a different direction now. I want to talk about math in real life and something fun today. But I do have us an assignment with that. Let me put it up on the screen, what we're looking at in Buzz. Yeah, if you got anything missing, got any zeros or anything, check that. But I think just about everybody, unless you just didn't get last week's turn in, you should be in good shape, because I didn't see a whole lot of missing assignments at all with you guys. You've done awesome. This week we have the golden ratio assignment. So we're going to look at this. The lesson is not in Buzz. This is something I have prepared, so I'm going to show you that. And then, like I said, with that semester final, it'll be 2 weeks from today if we need it. But if we go to activities, the golden ratio project, it has a lesson, but it only has one thing. So I'm going to switch over here because I've got the same thing over here. All right. I want you to look at these rectangles. These are all rectangles, different sizes, of course. And which one is the most appealing to you? Like if you were going to draw a rectangle, this is the one you would draw. I would probably do this one. Or this one looks right. That one just looks weird. It's too big, too long, too short, something, you know. Which one just makes you think, now that's. So I just want to take your opinions here. We're gonna talk about this because there have been multiple studies done over this. This is crazy how people talk about it. So I see H or G, B, D. Just throw your opinion out. There's no right or wrong answer. I just taking opinions there. F's getting some love. H is getting some love. Which just seems right. Like some of these just seem right. Some of these, like, yeah, I don't know about that. Like maybe is A too close to a square to really be called a rectangle? A square is a rectangle. Nobody really likes J. J just seems way out of shape, doesn't it? That just seems like it's like, all right, no, I don't. That doesn't just seem that appealing. But all right, everybody got your thoughts in. What do you like there? So we've got several votes. We're kind of in this range, it seems, for the most part. G's getting a little bit of love, but yeah, so kind of in this range then, I guess. All right, well let's talk about. We'll get to this rectangle. I want to talk about the Fibonacci sequence. You've probably heard of this. If you haven't, today's a good day for you. The sequence is actually 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. I can keep going. It's known as the Fibonacci sequence. Now, Fibonacci was this Italian dude. He lived like 800 years ago, 1170 to 1240. He is famous for promoting the Hindu Arabic number system in Europe. Like we use Arabic numbers ourselves, the 1 and 2 and 3 and all that. He's famous for his work in algebra, and he's famous for this sequence of numbers. His real name was Leonardo of Pisa. He lived in Pisa. And as a young boy, he would have seen the Leaning Tower being built. So that's when he is back when they were building what we know now as the Leaning Tower of Pisa. His father was named Bonacci, and so Fibonacci is son of Bonacci. So that's how he became known as Fibonacci. He never went by the name Fibonacci, but that's what history calls him because his father was named Bonacci, so son of Bonacci. But that is a Leonardo Fibonacci. And let's talk about this sequence because he didn't create this sequence. We don't create hardly anything in math. We discover it. He discovered this sequence of numbers. And this is how it works. You start with the ones, 1 and 1, and you add them together and you get 2. So then you take those two numbers, 1 and 2, and add them together to get 3. Then you take the 2 and the 3 and add together to get 5. So every time if you just add the last two numbers, that gives you the next number. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 1 is 34. 21 plus 34 is 55. And keep going. 233, 377. So the next number would be 610. Then the next number would be 987. You just keep adding the two numbers together to get the next one in the sequence. So it's not a real big secret on how the Fibonacci sequence works. You just add the two numbers. You start with two ones and you just go from there. That is the Fibonacci sequence. So if we illustrate that with a 1 by 1 square and then put another 1 by 1 square, then next to that we could put a 2 by 2. What's the next number? 3. There's a 3 by 3, then a 5 by 5, then an 8 by 8, then a 13 by 13, then 21 by 21, 34 by 34. We can just keep building out using the Fibonacci sequence as the side lengths. This is the length of the side of all of these squares, right? So these are length 1, 2, 3, all the way, and you can keep going from there. But this right here, if we take this and we start with the first square and we just connect the diagonals with a curved line, watch how this works. We just keep connecting the next square that we built with a curved line going diagonally across the square to where we have one continuous line that curves through every diagonal corner. This is what you end up with. Now there's a name for that red spiral. This is called the golden spiral. And this rectangle, and I'm talking about the big rectangle out here, is known as the golden rectangle because it's derived by using the Fibonacci sequence in building. And you saw how we built it. And it has been shown through many, many, many studies that this is the most pleasing looking rectangle to the human eye. Now, I don't know why, but for somehow we are attracted to this shape of a rectangle, pardon me, not triangle, a rectangle, the golden rectangle. And we're going to see that today, how that's been used throughout centuries. All right, so we have a length of 5 and a 5. So that means the root, the area is 5 squared, right? So 5 times 5. So this is a 25 squared units squared in the Fibonacci. The next one, we see that by putting these 1 by 1s inside there. There are 25 squares. So we know that 5 times 5 is 25 squared. And there are 25 squares in there. In the same way, if we went to the next square that we created was an 8, and it is 64 square units in the same way. That's how the squares work. So we can look at this, and I've kind of turned it upside down here. You start with these two ones down here, then you have a 2 by 2 and a 3 by 3 and a 5 by 5, 8 by 8. So that's the square dimensions of all of these. And so if we applied that into, I'll flip it over right here. There's area of 1, area of 1, area of 4, area of 9, area of 25, area of 36, etc. And if we compare these areas, look at the areas of all of these, just listing them straight down: 55, 89, 144, 233. If you divide the smaller number into the larger number that follows it, all of them are 1.618. Or that's dividing the larger one into the smaller one. Dividing the smaller one into the larger one is 0.618. If you go the other direction and divide the other direction, it's 1.618. And that will hold consistent throughout this series. If you look at the areas that are created by drawing that golden rectangle. And so if you find rectangles that the longer side compared to the shorter side has this ratio, right? You can see it's a 1.618 ratio when you take the smaller side and the larger side and you do the division. You find one of these two numbers depending on which way you divide it. That is a golden rectangle. And actually, the ones we were looking at, D fits that, and we did have a vote for D. That fits that description. This is 1.618 longer than the side. If the side is 1, and you multiply it by 1.618, you'll get this length right here. So that's why I put all those up there. And we were kind of in that range. We had some of folks like the H, a little longer one. Some liked a little shorter. But we were kind of around that range in this, looking at these right here. But that is a golden rectangle. And it has been used in nature. We find this Fibonacci sequence. Let's talk about the Fibonacci sequence: 1, 2, 3, 5, 8, 13. You can see that in the way that tree branches form or split. This will split into 2. And then when you get to the next level, it'll split into a third one. This one won't split, and this one will. And then there'll be 5 at the next level, and there'll be 8 at the next level, and there'll be 13. And it's just interesting how nature kind of follows. Like I said, we didn't create the sequence. Fibonacci discovered it. The main trunk will grow till it produces a branch. It creates 2 growth points. This pattern of branches is repeated for each new stem. A good example is the sneezewort plant, and you'll see root systems and even algebra exhibit this pattern. Algae, not algebra. Algae will exhibit this pattern. So this is something in nature, this Fibonacci sequence, that shows up time and time again. If you look at that golden spiral and the golden rectangle and put it over the Mona Lisa, look at the dimensions that he painted her with. Leonardo da Vinci painted. And if you look like her, from her chin to the top of her head, all of this kind of flows around what scientists have discovered is the most pleasing shape to the human eye. And artists know about this. Artists have, this was interesting that the Mona Lisa fits right inside that golden spiral. The Pantheon that was built by the Greeks forever ago, thousands of years ago, will fit that golden rectangle. Mostly look at the outside dimensions, the height, the edges, from the base. It's like the Greeks seem to know about. Egyptian pyramids seem to know a lot about the most pleasing shapes and how it fits into the dimensions of that golden rectangle. Look at the golden spiral. It follows the nautilus shell. Starting in the center there, it will spiral around very closely to that golden spiral. Even more amazing, look at a butterfly wing. That spiral's almost dead perfect as it goes around. The human ear follows very closely to that golden spiral. There's something to this Fibonacci sequence that makes things structurally work well, apparently, because we find it in nature. Oh, check this out. Hurricanes. You see those on the television where they have their satellite pictures of hurricanes. Galaxies. Look at the spiral of that galaxy and how it seems to just. So there's something in physics with this Fibonacci sequence that Leonardo of Pisa figured out and somehow came up with this sequence of numbers that just works in nature. It's kind of crazy, but it's really cool how, we didn't have to invent math. We just had to figure out it was out there. Even look at DNA. Here's the very stuff that we are built of. And if you take a DNA and take the width and then look at one full cycle where it loops and then loops back to where it started, the length of the DNA divided by the width of the DNA, 1.618. Boy, I tell you, if there's not something to this, this is crazy. There's really, really something to this with the Fibonacci sequence. So here's our activity you have for the week. Here's your assignment this week. You'll need a tape measure, a ruler. You're going to try to find 3 things out there around your house that represent a golden rectangle or a golden spiral. It could be items in nature, it could be architecture, it could be logos, it could be art. It doesn't have to be at your house, it could be out in your community. If you find golden rectangles, submit the pictures along with the measurements. Say, look, this is about 1.6, right? You're not going to be able to measure 1.618. But if it's about 1.6 compared to the width, 1.6 times the width would be the length. See if you can find at least 3 items out there, because advertisers seem to know about that. If you have a golden spiral, you don't have to measure anything, but you can look to see, oh, that's this golden spiral. There is a lot out there that meet this. I want to show you. Let's see, do I have anything? Yep, that's all the pictures. Okay. I want to show you this real quick. This is a 2-minute video talking about the Fibonacci sequence and the golden rectangle. So I'm going to switch over. There it is. All right, check this out.
Hi, I'm Doug Pat, and this is How to Architect. The Fibonacci sequence, the golden rectangle, and architecture. In 1202, Leonardo Fibonacci was famously investigating rabbit reproduction and made note of a sequence that is now known as his namesake, the Fibonacci sequence. The sequence is a series of numbers derived by adding each number to the previous. That is, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, etc. Plant leaves as a spiral around a stem, called phyllotaxis, in some cases follow a mathematical rhythm of 1.618. That's the same spiraling numerical rhythm seen on the skin of a pineapple, as well as the seed head arrangement of the sunflower and the base of a pine cone. In geometric terms, if a rectangle is drawn with one side equal to 1 and its perpendicular represented as 1.618, a desirable shape emerges. In 1876, Gustav Fechner did a study that determined people visually preferred the shape to other rectangles. It's thought that the ratio may have been used as early as the Egyptians in the creation of the Great Pyramids. Based on measurements of the pyramid at Giza, the hypotenuse almost precisely matches the number phi, or 1.618. It's also thought that Andrea Palladio employed the golden ratio of proportions. This is his Villa Rotonda, outside of Vicenza in northern Italy. Even the modern architect Le Corbusier used the proportions in his modular man study and, most likely, in the design of his Unité de Habitation in Marseille, France. If you're looking for more videos about the golden rectangle and architecture, just click the link in the description box. I'm Doug Pat. We'll see you next time.
One thing I'll show you, because when I say advertisers know what the golden rectangle, what's appealing to the eye, and you're like, oh, Mr. Brock, I was going to use that. Look, let's check out a credit card, because it's like, oh, you want a credit card, right? Let's see. I'm going to measure in millimeters because I want to get it as precise as possible. That looks to be right at 53 millimeters. Okay, 53 millimeters. So let me put up this real quick. 53 times 1.618. 85, a little over 85. All right, let's try this then. All right, I'm going to try to get this up where you can see it. Let's see about how long. Just a hair over 85. It looks like, get that right on the zero. Just a hair over 85 millimeters. Credit cards are the golden rectangle, should be pleasing to the eye, should make you want to get a credit card. Yes, advertisers are very much aware of the golden rectangle and what is appealing to us as people. Advertisements, a lot of logos of companies may fit that golden rectangle dimensions, with the logo is 1.6 wide compared to its height and all that kind of stuff. Tons of stuff out there. You can find videos to find all of that. It's really cool how math is out there. We just discovered it, guys. We just discovered it. And this Fibonacci sequence seems to be down to the very core of everything. Considering our DNA matches that same dimensions, and it's just wild. It's all over. So there's something in physics about that. Must be a solid structural dimensions for things to really work well, especially since like the Pantheon's still standing after thousands of years for the most part. But that's what we have this week, guys. Just put it on a Google Doc, take 3 pictures, put them on a Google Doc, and just submit them in Buzz. Easy points. You know, a golden spiral, a golden rectangle. If it's a rectangle, try to put the dimensions, say I measured it and this is the measurements I got. It's about 1.6. Like you're probably, like, again, you're not going to get 1.618 exactly, but check the width and the length and see, yeah, that's about 1.6, just right at it. So have some fun with this, guys. You may amaze yourself figuring out how many things out there fit those dimensions. So a lot of, you can find stuff on the internet, find stuff in the community, find stuff in your house, and just play with it this week. So otherwise, we will have class next week, guys. So I will see you then. I'll be here Thursday if anyone's got any questions. If you're missing anything, and like I say, hardly any of you are missing anything, get that turned in, and then we'll catch you later. So have a great week.